Right, so we are in session 8. We're going to look at a specific model to understand a little bit how building models work. And good part of building a model will be to understand the components that are needed in order to build it, and some good understanding of the impact that changes in parameters that govern the components have on the overall outcome. We'll end up with some model simulations. So the sort of the ultimate goal, of course, in having a computational representation is that we can do simulations, that we can test hypotheses, can develop new hypotheses, and make quantitative predictions. So that will be the program for today. And let me start by introducing the model that we are going to look at and give you a little bit of a background on how this all came into being. So Brian Goodwin, who did that, you can find a paper, and this is from 1965, originally talks about oscillatory behavior and enzymatic system in the title. And what he had in mind as even though he was a biochemical researcher, he had taken some inspirations from engineering. And this inspiration he turned into designing a model that would use control strategies that engineering had thought they had invented, but that many people in the last century suspected living systems had been employing for a long time already. So I came up with this scheme that you see here on the screen. And it's a screen that is a scheme that starts looking at a so-called reaction chain or regulatory chains. So things starting with one component, you called X, and then somehow that leads to another component, which is called Y, and another component Z, and that could in principle go very long. And in biochemistry has been called pathways, like metabolic pathways or signaling pathways. And so events where one thing leads to the other, and it's based sort of on this idea of production lines. You need to synthesize something, it involves a couple of steps in between, or you want signaling to reach a certain final target. You need to signal from one to the other, first, second, third messenger, and so on. And also in gene expression regulation, you have one gene that regulates the next and it regulates the next and so on. So cascades, if you like. So what Goodwin then took from engineering is that if you wanted to have a regulatory impact on this pathway, on this cascade of events, so you wanted to have some way for this system of things that work to self-regulate. Right, so the idea is then in a living system, there isn't an engineer watching over it who can then sort of tune how things are going and observe everything. But the question is, can the biological system do it itself? Like, can a bacterium regulate its own behavior? Well, of course it has to. There's nobody else to help. So he then came up with this idea, well, in engineering, we use feedback control, and feedback control means that something downstream, and like this component Z, for example, here, has some impact on a production that goes on upstream. So something at the end of the production chain, something that is needed or wanted, target, has an impact on what happens at the beginning of this production line. And yeah, you can see in a typical engineering fashion, this little square on the left-hand side here that is put in between this dashed line shows what you want this feedback to do. So feedback means somebody down the stream has an impact upstream, and how this feedback is shown here in a mathematical function. So that function shows that what you have on the horizontal axis Z, so the amount of the target or that last member of this cascade, and a function of Z is what do you want it to do with the production of the first member X. So how does it impact the production of X? And this function, you have now had a lot of introduction into linear and nonlinear functions. You've also seen the Hill function, the sigmoidal function, and maybe you recognize it here if you make a mirror image of what you see here. So the inverted sigmoid, meaning that if there's a small amount of Z present, so this concentration, say if we interpret it as concentration of Z, if that is small, so close to zero at the beginning, then it means that the production of this first component X goes on at a high speed, or there's good production going on. And then the higher you go with X, and this production speed, or the rate of production of X reduces slowly, and then it drops suddenly until for high concentrations of the target, you will see low production speed and production that eventually mathematically could even come to zero, so would be stopped altogether. So that's the idea. And of course, you can intuitively understand that if you want a certain amount of target and you have too little of it, what you want to do is want to speed up the production. So that's the first part of the sigmoid. And once you have enough, you want to reduce the speed of production. If you have too much, you want to actually reduce the production such that it decreases again, following sort of this reporting back of what's going on to the beginning of the production line. So that's how this was envisioned. And if you read the paper from 1965 by Goodwin on how he interprets this, what he actually had in mind was, among other things, the control of metabolic processes. So here's the title, Oscillatory Behavior and Enzymatic Control Processes, 1965. And he also wanted to show that once you have this control implemented, you can do also more surprising things, not just keep a certain amount of a desired target, but also to self-regulate regularly recurring events like oscillatory events, which led him to propose this also as a model or as a functional principle for periodic processes like circadian rhythms, which are displayed here as an example. So that's in recording of glow intensity in Goni Aulax, a glowing marine organism that shows a circadian behavior even in the absence of any changes in light or temperature. And so the circadian clock, the internal clock that keeps ticking even without any external clues, is one of the applications of what we are doing here. Right, so after this historical introduction into this principle of why negative feedback might be a useful thing to have, and we now try to go into building a model where negative feedback is an integral part and which achieves the goal of regulating the final outcome of each of the components in the chain, and then leading to also oscillatory behavior if that is something, if recurrence or rhythmicity is something that is wanted. So from a mathematical point of view, in the slide that we are seeing here, we can see a formulation. There's a couple of differential equations. You have seen differential equations before, but I'll just briefly tell you what are the components that Goodwin proposed And one of the nice things about this model here is that it's the simplest that you can imagine. It's simple in the sense that almost all components in that model are linear. So it's just a very simple way of setting it up, and there's only one nonlinear component. So if you look at the equations on the left-hand side, these are rate equations. So the left-hand side says a rate, and the interpretation is how does the rate of production or destruction of a certain metabolite or molecular entity change over time. Right? So it's a dynamical approach. You have something that is fine, but does it change at all? It cannot change if that rate is zero. If it's positive, it will increase, and if it's negative, it will decrease. So we have three components. And sorry for the purpose of doing everything here in MATLAB. I have to sort of switch from XYZ to X1, X2, X3. So our components are now called X1, X2, X3. There are three different molecular species. And the rate of the first component is composed of two terms. The first is a very complicated nonlinear term. We'll look at this in detail. And the second is just minus K1 times X. It's just the concentration of that molecule, X1, times a parameter, times a number. K was called K1, a rate constant, if you like, but it's just a number. And it's negatively, so the more you have, the more it will be reduced. So there's a self-regulatory means already. And it's called the first order decay term. And you can see a similar decay term is also in the equation for the second molecule and for the third molecule as well. So then the next thing is the second molecule, in addition to having this decay term, also has a production term, which means its rate of production just follows whatever you have of the previous molecular species. So K1 times X1, K1 again being a number and X1 being the concentration of X1, one that we called X previously. And in very similar structures, set up the third equation, just the same thing, just changing the indices. So the rate of the third depends on the production proportional to the amount of the second, minus degradation or destruction based on the amount of itself, X3. And then we have this feedback term, and now comes the negative feedback. So how do we implement negative feedback at all? So the first thing is to notice that negative doesn't necessarily go along with a minus sign in the equation. Negative feedback means the rate is impacted negatively, right? So the rate, overall the rate is impacted negatively. So there's something that will reduce the rate here. And how does it do that? So in the differential equation, the negativity, the reduction is achieved by division. So we divide by something, and the larger the number is by which we divide, the smaller the overall impact will be. So we can see here this division, this forward slash indicating division. So if we, for the moment, if in the first step we ignore the denominator and say all this down here somehow equal to 1, we just ignore it for the moment, then the production will depend on K naught. So this is sort of a default production rate at which this molecule X1 is being synthesized. And you can also divide it by Km, which is another number. And then comes the question, how does this negative feedback come into play? Well, it is by dividing this production that you have here sort of set as a default, and then divide by something that depends on the amount of this molecule called previously we said Z, but here it's X3, so the third member in that cascade. Right, and how do we divide? We multiply x3 with a number ki, sort of an inhibition constant. If you look it up in tabular form, a sort of a factor that says how strong is that impact of that molecule on the production. So if it's very small, if it's zero, it's not there, right? If it just multiply with zero, there will be no impact. If it's small, there will be a little bit of an impact. And if that's a large number, there will be a strong impact because you multiply with the amount of x3. Furthermore, and something that reminds us of the Hill equation, if you remember how the Hill equation was set up, there's an exponent here, so which is nothing but a mathematical trick, namely to have impact on the shape of that feedback function. And it's called n, it's an exponent, it can be a rational number, so it can be an integer, but it can also be anything between 1 and 2, or 2 and 3, or 3 and 4. And it doesn't have a literal interpretation, although very often it is interpreted as having to do with like allostericity or multiple binding sites in the target. So what we need to remember is that we have one complicated function that we investigate before we use it in the model, and some trivial, fairly simple function that otherwise form a system now that is a total of 3 differential equations. And they are all coupled by means of this nonlinear term at the beginning here. So everything depends on everybody else. It's a small network, if you like. Thinking back of the very early sessions of the course, and then these parameters k naught, ki, n, and so on, they have some interpretation. We'll treat them in a very simple fashion here, but then if you go into a real application, like you're wanting to predict a system, an experimental system, then you would have to specify these in detail. And finally, before we go into the MATLAB implementation, just to show you that at the bottom of this slide, there's an algebraic formulation for importing it into MATLAB. So you can copy and paste if you like, where on the left-hand side, the rate is now, you can see it's composed of 3 terms. And so you have one name, one variable that captures all the species that are there, and you identify the first, second, and third by putting the number in parentheses. And then on the right-hand side is the same thing that we had before, just in a MATLAB-y fashion. Right, so with this, we go into coding. Now setting up, first of all, the feedback function, study the function, then look at the steady state solutions of the model. What is the expected solution under the condition of no feedback and yes feedback? And then we do the full model and some simulations with different settings of the rate constants and the other parameters. Yeah. Okay. So I have set up a template for this. It's also in the script that you can download, just to avoid a little bit of too much writing. And I have put in a reminder at the top. So in green is just commented something that reminds us what the model should look like. And this is the way in which we want to deal with it. And I've put some values for the parameters, just some suggested numbers. They're fairly arbitrary, but this is a starting point to deal with. As we're not going into direct comparison with experimental data, we can as well use those numbers here. So let me just do some changes. Take the video off because we don't need that. And now with this model here in mind and parameters as given, I think I simplify that a little bit by putting everything into a single line. So then we have more space. First thing that we want to do is we now want to take those parameters to define the feedback function. So let's do that. We have done that multiple times. Feedback feedback, what do we call it? Feedback inhibition. So that's the name for our function, and we can equal that with, we do an anonymous function, and what is our variable? So our variable, of course, the one that we are interested in for to understand this function is the third variable, so the feedback variable. So we would put that in parentheses here and call that x3. So this is the thing that we want to study. Remember that little square with the function, with the sigmoid function. That's something that we want to now reproduce. So we get this as a function of k naught, so we do it k0, k naught, and then divide it by something in parentheses, and we have km. I'm just copying for what I wrote up there, plus k sub I, that's the inhibition constant, multiplied with, and the third variable was called x3. So now comes our x3 and to the power of n. Hopefully you can see that well on that screen. So this is just what I have written up here. I just sort of copied and pasted down here, except the only thing I did is I put the dot operator before the division and the power of sign. And you might remember that from previous sessions. That refers to element-wise operation. Okay, and then we have our feedback inhibition function. We can execute the code. And we can see how that works. So here's the function handle. So that defined our function, and we can now go and work with it. Note how we have specified k naught, km, ki, and n. So these all have specific values, and they're not entering as variables anymore. And then was our recipe to get such a function plotted. It's always the same. You define some limits. I define 0 to 10, so we have the range of the amount of x3 that goes between 0 and 10 arbitrary units. And then within those limits, we want to use fplot, the function plot, to plot what we have. So a function called feedback inhibition. So we can just use that, and we can plot it within limits. And what was the thing? There was this thing about the line width. So line width in MATLAB can be specified. So I have added, if I just go back to this, line width is the argument that helps me make the line thicker. Take this away. So here's our graph. The graph is a decaying function that starts from 10, and it's a hyperbolically decaying function that is showing that on the right-hand side we have, no, on the horizontal side, going to the right, we have x3, the amount of our regulatory molecule, and on the vertical axis we have the speed of production of the first variable x1. You can see the speed will be the smaller, the more amount of x3 we have. So it's not what we wanted, it's not what we had in the little square that Goodwin displayed for his original paper. However, these things can be achieved quite easily if I do something, namely I copy and paste this code here. And I now, after having copied and pasted this, I now change the amount of n. Remember, n was the exponent. So let's put it like this. That was 1 in the simulation that we just did. And if we change that to a number that is larger than 1, for example, set n equal to 5. So we now have x3 to the power of 5 inhibiting the production of x1, or in that term. And if we repeat this thing, we just give it a different name. We call that feedback function 2, feedback inhibition 2. And so we have a new feedback inhibition defined after changing that parameter. And we're plotting this on top of the previous one. So we have to say to keep one. Let's hold on. Want to keep the previous plot there. And then let's see how that works. The figure should be somewhere in the back. Is it still there? Here's the figure. That's what it looks like. So now we have the plot with n equal 1, the blue one, and the plot with n equal 5 is the red one. I think I don't really like it going to 10, so we might just as well let it only go to 5. Can we have that going to 5? Just put that away, make a new picture. No, that still goes to 10 because I have not changed it up here. So I shouldn't redefine the limits. So that was a nonsense to do. I just keep the same limits for both functions. And then if I plot it again, it's a little bit nicer. Right. So I can add a legend, and the legend is, no, it's not this one. Is n equal 1 is the blue curve, and n equal 5 is the red curve. So now we know which is which. And you can see the red curve, of course, correctly reflects what we wanted, namely small inhibition or small impact of X3 on the production of X1 for small concentrations. So it stays high until about, I don't know, something 0.7 or so. And then for very large concentration, it's near 0 or nothing. So it means the production is blocked. And in between, there's a region of sharp decline. So if you think this a little bit further, if n was even larger, so not 5, but say 10 or 20 or 100, you should do it immediately. Try in your own code what that goes to. Well, let's just do it. Let's just do it and put it equal to 10. What happens? You can see the change. The higher the number n is, the more this becomes a step function. And this is the idea of the negative feedback control, that you control the incoming process production of X1 with a step function. So you say you have a high rate for small concentration of X3, you have a small rate for high concentrations of X3, and in between there's a steep decline, so a region where it switches. So we have implemented a step function by means of this exponent. And you remember from the Hill function that this is not an unrealistic. This is something that is actually very widely observed in biochemical, genetic, regulatory processes. And the interpretation being, of course, that also within biology, there's a need for occasionally switch from one type of feedback to another. And this is the way how it can be done. So I'm not saying it is done in every case like this, but this is one way of implementing this control principle in terms of supposed biochemical reactions, be they metabolic, gene expression, regulatory, or signaling. Right. So what else can we see here? Well, maybe just as a final remark, if you think that sounds like something very specific, it's not specific. It's a very generic principle, this kind of switching behavior. And if you ever look into the details of how artificial intelligence work, they are building on the so-called neural networks. At the heart of every single neural network that's simulated in billions and billions of implementation in this moment, any of the machine learning or AI algorithm that runs is working with this kind of step function. It's probably implemented somehow differently as tangens hyperbolicus or other mathematical forms, but it's this switching behavior that helps you build up nonlinearity in a way that helps you also to model just about any behavior that you would like to model. And also if you think of the biochemical system, to get a repertoire of behavior that helps you adapt to any environmental challenge that might come along your way. Okay, so that was the function. Let's have a bit of a space here. Double percentage means make a new cell. And what we're now going to do is we're now implementing the model and having a look at its steady state solution. So what state will it end up? And we can have a look at without feedback inhibition, but also with feedback inhibition. So let's try to do that. The function, the model function can be defined. We can call it f or whatever you like to call it. Now we need we have a new function, so we say what is the variable for now, not a single function, but the whole system, the whole Goodwin model of three differential equations. So I give it a different name. I call that capital X. And the capital X is now a vector that will comprise all of the variables involved. So x1, x2, x3. For three equations, we need to define those three equations. We put them in an array. And what we can do, we can, I keep writing this incorrectly, it's called feedback. Inhibition, what did we call it? I forgot what it was called. Feedback inhibition 2 was the one that we had defined with that exponent that already had the nonlinear regulatory properties. And of course, when we refer to this function, we need to say which of the variables should it call. From these equations, from within these equations, it should call the third one, which is x3. So feedback function, that function that we defined before, but applied to the third variable of this model of differential equations. And if you remember, so I think I need to close that second pair of parentheses here. Now it's open, close, open, close. And if you remember, our equation comprised, we just go back. Here's a simplified form. I have set all the parameters that were there apart from those that we looked at equal to 1 minus x1. So this is the most primitive way of setting up the Goodwin model. So we can call that minus x1. And you remember this is an artifact of having that parameter set exactly equal to 1. And then comma next equation. And that was then defined by x1 minus x2. If I get it right, x2 minus x1 minus x2 in the most primitive way. And the last equation was x2 minus x3. So if you want that written more nicely, you can also put that into 3 lines with the triple period at the end, but let's just have it here. So we can have first equation, feedback function minus x1, second equation, x1 minus x2, third equation, x2 minus x3. And this is the function, and we remember that we're now using feedback function inhibition to actually, you know what, I might just bring that back with the parameter so that we have full control of it. So I just copy and paste what we had before to say this is how we're doing it. So we're setting up constants, we're setting up the feedback inhibition, and then we're using it in the context of this model. So now we want to find the solution of this equation. Why do we want that? Because a solution of the equation in mathematical form, if nothing else is specified, means the equations all go equal to 0. So they are set, first equation equal to 0, second and third set to 0. So we get this by a function called fsolve, and we apply fsolve to f. The only thing that we need to do, we had that several times, just get these hints from MATLAB away. We need to specify some numerical values to start with because it's an algebraic solution that will sort of approximate it numerically internally when you call this function. And so you need to give some starting points and just some arbitrary numbers, 1, 1, 1. So that's initial conditions for each of the variables involved. And if we did everything right, we should then get a solution. But let's first check whether this is what we want to do. So what we want to do is, and I mean in terms of the parameters. So we know most of the rate consts now have been set equal to 1, but we have k naught, which is the input here. And we have the km, which we just leave as it is. But then we have the strength of the inhibition. Let's just, for a moment, take the inhibition away by setting Ki equal to 0, right? No inhibition if that is 0. And 10, let's put that equal to 5. So the sigmoid, that was a nice smooth sigmoid that we saw in the previous simulation. We'll work with 10 as well. Right, so we have it all set up, except there is now, in this version, there is no feedback inhibition. And so we see what is the generic solution of this model of a production line comprising 3 steps in the way indicated by this equation. And what we can see, I have executed the code at the bottom in the command window. You can see my result. For each of the species, the number is given. The steady state equation is 10 for x1, 10 for x2, and 10 for x3. The fact that they are identical is an artifact because I chose these rate constants to be equal to 1. So it's all very symmetric. So this is a little bit of a mathematical symmetry that I have imposed by choosing specific numbers. It will in general not be the identical number like 10, 0, 0, 0, and so on, as you can imagine. So nevertheless, we get the solution. So this is our starting point. When no inhibition, no feedback inhibition takes place, then this is what we expect for this model under these conditions. And now we're setting some 0.1 or some value where Ki, the constant of inhibition, is non-zero, is positive, and so there will be an impact. So now the sigmoid. Now the sigmoidal regulatory feedback will take effect. And if we do that, we get a different number. We get the number of 1.4, 1.4, 1.4. Again, it's the same, but it's now a value that is with feedback control. So what you see is that the steady states, so the states where this equation is solved, the solution of the model is now at a lower state. And because this is a concentration, it means also there will be less present of each of the amounts of each of the components of that production line. And as you can imagine, if you have then different values of the inhibitory strength, you will be able to set the value that you would like to have if you want to do that. Right. So this was the way to treat any model. It's a generic way. We're not going to do this much more because we're not really going to look into very much more detail here. We're going to go to simulations of the model, but there are ways for sufficiently simple models using fsolve that you can just mathematically find out what their steady state solution will be, what will they be ending up if you just let it run. So it means if you had it happening in a real world environment. Okay, and having seen that, how the model works without inhibition, how it works with inhibition. So the inhibition reduces the amounts of each of those values. Let's now have a look at the temporal evolution, meaning how does this model evolve over time and what features are there depending on different settings of those parameters that we have already investigated. So now we need to define our model, but we have our model defined, right? If we look at it, we have here, actually, we have the model defined as a set of three differential equations, first, second, and third. And we have set up the parameters. And we know that we also need some numerical values for each of the species or concentrations in order to start a numerical simulation. So if we now, for the moment, forget about this F solve here, saying no, we have completed this, I just make it a comment here, we can now go on and try to run a simulation. So I'll do a simulation as we have seen it in previous sessions 5, 6, and 7 of the course. We're using a solver called ODE 45. And however, I'm going to set it up slightly different from how it was done there to show you how one thing in MATLAB can build up on the previous thing. So if you remember how to do it, we need, for every simulation, we need to define the time range. And this will be an array in square brackets, which has the starting point and the end point. So I say 0 to 20, we'll check and correct that later. This is the time period over which we want to simulate two, well, initially arbitrary numbers. And then we need to define our initial conditions. So let's define one for the first. X ini, we don't know, we have put it to 1 before, it can be 0.1, whatever. This is arbitrary for the moment. We can adjust it later. And so that's the initial condition for the first species or component, and we can just copy and paste it and define initial conditions for the other set as well. And you can make them identical or non-identical, doesn't really matter. Sometimes when doing simulations and we have sort of mathematically very symmetrical set of equations, and you saw it before in the solutions, we have a couple of constants were just made equal to 1, just arbitrarily. We don't like to take identical initial conditions because that might result in odd behavior due to that symmetry only. So if you make them slightly different, or you use the random number, oops, no, that's not what I wanted. If you make them slightly different, or you have them generated by the random number generator, then it will make sure you will get sort of more generic starting conditions. Okay, and now we want to simulate that model. And so if you remember it, we need the time and we need the variables. All variables have been what's called X. Doesn't matter. We need the time and the variables. So 3 variables that we have, and we'll get that back from simulating using ODE 45. All arguments go in round parentheses. And let's have a look at what we need. We need the model, we need the time period, and we need the initial conditions. So what is our model? We have to go back a little bit up. Our model is defined and it's a variable called f. So let's put it and let's say, take that model, and this is the variable called f. Now you might remember that in the last session, what we did was to define the model as a function, and then we could refer to that function using the @ handle, but we have that already sort of accomplished by defining our function here. Here's our @ handle. So now we can just refer to that variable directly, and it will use the one that we have set up in the code above. And then we need the time period, it's called time, and then we need those 3 initial conditions. We just put them together, x1 ini, x2 ini, x3 ini. right? So these are our three initial conditions, 1, 2, 3, and a semicolon will suppress any output at the end. So here's our simulation set up. We have the model F, we have time period, initial conditions, and then we can do, and I think the only thing is missing to make a plot. So let's define a figure. We already had a figure. If we want to keep that, let's define figure 2, next figure, and then plot what we have, plot time versus variables. Run the code, and there's something wrong here, so we have to go back and go debugging. Ki equal 1, and then we're using feedback inhibition. I need to copy over the function, feedback inhibition function. We need to call it again in order to have it specified with the new conditions. And then we get a simulation that shows us if there's no feedback inhibition present. And we remember the result that we get analytically before was 10, 10, 10. Now we have the simulation of going from arbitrary initial conditions to final values that are equal to 10. And if we put in the legend, data 1, 2, 3, so that's variable x1, x2, x3, just put it in, x1, x2, and the last one is x3, then we can see that the blue one rises first. That's the first compound. The second rises second, and the third rises last. Going to 10 means going to a high level because, of course, there's no feedback inhibition. There's nothing that sort of brings concentrations down again. If I take this away, if we now go change our parameter, set the feedback inhibition to some value, and we started 0.1 before, repeat the simulation. What we can see is we can see that now, first of all, this is brought down to much lower levels. So simulation brings down the overall levels of each of the components. And we see so that this bringing them down follows an initial strong rise here. So x1 goes up to values near 6 and then falls down again. And similarly, the second and the third variable do this. So we see an approach to a much smaller overall level of each of the compounds in an oscillatory fashion. And if you don't know where that comes from, we can actually test it where this comes from. And the question is, what does it have to do with the nonlinearity of the model? And you remember the nonlinearity was introduced by dividing depending on the concentration of x3 to the power of n. So this n is here set to 5. And we remember that being a sigmoidal function is critically depends on n being not equal to 1 or being larger than 1. So what if we go back and simulate our model with a linear implementation of that x3, namely x to the power of 1 only. And if we do this simulation, we can see now most of this oscillatory behavior is gone, and we're ending up with a damped oscillation that's just an overshoot initially, transiently, and then reaching a final steady state level for all three components. So now you can sort of continue having all implemented this, understanding each of the components and knowing how to analyze the function in isolation, using it in the context of a model. You can go ahead and make predictions, and I'm not going to do this in the script that you can download. There are a couple of examples. Let's just do one more simulation because we had it before with a very steep sigmoidal function. You remember the larger n was, the steeper it got. And we have our previous simulation used n equal 5. If we now use n equal 10 and repeat the simulation, what you can see that the damping has sort of been weaker and weaker. So from 1 to 5 to 10, the damping became weaker. And if we now simulate this for a much longer time period, just taking 100 instead of 20 that I used before, you can see this rhythmic behavior never dampens out. So we're ending with a model that actually not only shows feedback regulation and the possibility to control levels of those members of the production chain or cascade here, but also can lead to an entirely new behavior, namely a rhythmic repetition of a pattern that is entirely autonomous. Right? Autonomous meaning I never said do something repeatedly or go up, go down. I just set parameters equal to values. And yet it starts to maintain this oscillatory behavior. And after some time, this is stable and doesn't increase in amplitude or decrease in amplitude. It also doesn't increase or decrease in frequency. So that was the second finding that Goodwin reported, that using control terms, first of all, you know how you can manipulate the outcome, so you can adapt to different environmental requirements or restraints, but now surprisingly also that this can lead to entirely new types of behaviors like oscillatory behavior or structured behavior in time. If you expand this, you can also find that this leads to behavior like pattern formation in space and time. This is then applications like the developmental stages in Drosophila eggs in the larvae, where different proteins start to form patterns of expression that lead to development of limbs and heads and tails and so on. Right, and with this outlook of this very simple model with very profound consequences, I'd like to finish today's webinar. It's also been, I think, my last MATLAB webinar. So from now on, every teaching is going to be using the language called Python. So it's also a change in the way that my teaching is going to be. Thank you for watching. And we have some more videos already on the webpage for the next sessions, which are then dedicated to another programming language, which is R, and then a totally different topic, which is to do with data analysis. Bye, and good luck with the rest of the course and the mini project.